In the field of artificial intelligence, particularly in training large language models, selecting the right mix of data for pre-training is a major challenge. Pre-training datasets, like those from Common Crawl, are vast collections of web content that offer incredible diversity but come without clear labels indicating specific domains, such as science, literature, or social sciences. This makes it difficult to curate an optimal data mixture that balances general knowledge with specialized expertise. Manually labeling or curating these datasets, as seen in projects like the Pile, is extremely labor-intensive and doesn't always lead to the best results. To tackle this, researchers have developed CLIME, which stands for Clustering-Based Iterative Data Mixture Bootstrapping. This is an automated framework designed to discover, evaluate, and refine data mixtures for language model pre-training. At its core, CLIME works by first embedding large-scale datasets into a semantic space. This means it represents the data as points in a high-dimensional space where similar content is clustered together based on meaning and context. For example, documents about mathematics might cluster near each other, while those on history form a separate group. Once the data is clustered, CLIME enters an iterative search process. It uses a smaller proxy model, a lightweight version of a language model, to test different mixtures of these clusters. A predictor component then assesses how well each mixture performs on specific tasks or benchmarks. This process repeats, refining the mixture over time to find the most effective combination. The goal is to maximize the model's performance without wasting resources on suboptimal data. In their experiments, the researchers trained a 1 billion parameter model on 400 billion tokens using a mixture identified by CLIME. This resulted in a 2% improvement over the state-of-the-art LLAM A3.2 to 1B model. That's significant because even small gains in performance can make a big difference in real-world applications, like chatbots or content generation. They also found that when they optimized the data mixture for a particular domain, such as social sciences, the model improved by up to 5% compared to randomly sampling data. This highlights how targeted data selection can enhance domain-specific capabilities. The paper emphasizes the importance of the final stages of pre-training, often called mid-training, where models are fine-tuned on high-quality, targeted data. For instance, previous studies have shown that emphasizing domain-specific datasets boosts performance on benchmarks like GSM-8K for math problems, MMLU for reasoning tasks, and Human Eval for coding. CLIME builds on this by automating the process, making it easier to achieve these gains without manual intervention. To make their work more accessible, the researchers introduced two new resources. First, there's CLIME Lab, a filtered corpus of 1.2 trillion tokens organized into 20 clusters. This serves as a research playground, allowing other scientists to experiment with clustered data mixtures. Second, they created CLIME Mix, a more compact dataset of 400 billion tokens that's specifically designed for efficient pre-training. When used under the same token budget, CLIME Mix delivers superior performance compared to other datasets like Nemotron CCHQ or FineWeb Ado. The paper includes comparisons that show CLIMB's effectiveness. For example, when pre-training a 1 billion parameter model on CLIME Mix, the average performance across 12 downstream benchmarks scales better than with random sampling or other baselines. A figure in the paper illustrates this, plotting performance against training tokens, where CLIME Mix consistently outperforms alternatives as the token count increases from 80 billion to 400 billion. Delving deeper, CLIME addresses the limitations of existing datasets. Common Crawl, while massive, relies on broad filtering methods like perplexity scores or educational value heuristics, which don't always capture the nuances needed for specific domains. In contrast, CLIMB's clustering approach ensures that the data mixture is tailored to the model's needs. The researchers analyzed the final data mixture and identified key characteristics of an optimal one. It should include a balance of high-quality, diverse content with enough emphasis on underrepresented domains to avoid biases. For practical applications, imagine you're building a language model for educational purposes. With CLIME, you could automatically identify and mix clusters of data related to science and history, ensuring the model excels in those areas without overloading it with irrelevant web noise. The framework also demonstrates a better trade-off between model size and performance. In comparisons with other state-of-the-art models, Climb achieves higher scores on general reasoning benchmarks while using fewer parameters, making it more efficient for scaling. Overall, this work underscores that the quality of data mixtures is just as crucial as the quantity of data in pre-training. By automating the process, Climb paves the way for more efficient and effective language model development, potentially leading to advancements in areas like specialized AI assistants or domain expert systems. The datasets and code are available on Hugging Face and their homepage for further exploration.